Mr. Tarrou. In this math lesson, we are going to be looking at the counting principle, permutations, and combinations. You might be getting introduced to these in Algebra 2 or pre-calculus, maybe the beginnings of a probabilities class, and we do use these extensively through the probability chapters in AP Statistics, another class that I teach. We are going to build the understanding of the counting principle through building a car, choosing from different colors and types of engines and transmissions using a tree diagram. These are really, really nice if you want to find, well, number of combinations. Or, since that calculation is actually pretty simple, ultimately, this is really good if you want to find the probability of a sequence of events. We do this in probabilities and AP Statistics. After we have a good understanding of what the counting principle is, we're going to play the lottery. And I'm going to come up with a lottery game that's close to what actually my state uses and, try and figure out the probability of, us winning the lottery if we buy one particular ticket, or just one ticket. I don't know why I said particular. And through that discussion, hopefully help you understand the difference between permutations and combinations. And after I hope that you have an understanding of that, I'll go ahead and give you the formulas for calculating these two and work through two more examples at the end of the lesson. Now, I don't think it's a great idea to just have a formula and have numbers coming out of it you don't completely understand, but if you do want to skip ahead to the examples, the timestamps will be in the description of this video. So we want to buy a car. Now, we're at the lot, or we're just on the internet at a car building site, and we find that it comes in 5 different colors with either a straight 4, V6, or V8 engine, and it'll come with either an automatic or manual transmission. I like manual transmissions myself if I'm driving a sports car. How many unique cars can you choose from or build on this site? Okay, now you can see, because I already have the notes written on the board, that it's a pretty simple combination. We're going to be able to build 30 unique cars. But if you didn't know the counting principle, then you might want to build a tree diagram to help you understand or why there are 30 unique cars you can build with this particular setting. Well, if I look at just the automatic transmission, with that auto, we can have a 4-cylinder V6 or V8, and with each of those engine choices, we have white, yellow, purple, blue, and orange, simply because that was the colors of chalk I have that show up the best on this green chalkboard. And again, you have all those same color choices for V6s and for V8s. Now, if I go to the end of my tree diagram, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 possible cars I can build. And that's coming from the 3 choices that I have for the engine, along with the 5 color choices that I have on our board, and that would be 1 times 3 times 5, which you can see, the beauty of the tree diagram, that there are ultimately 15 combinations. Now, if I come through here, though, and say, I don't want an auto, I want to use a manual transmission, well, there's another 15 unique cars you can build with a manual transmission. So you have 2 times 3 times the 5 colors gives you a total of 30 unique cars you can build for this particular model. Now, that's, of course, you can have fancy wheels and plain wheels, and you can have, adaptive cruise control. There's all kinds of choices we have for building cars now, but in this simple example, there are 30 unique cars. Now, you don't want to make a tree diagram every time you want to find out how many unique, like in this case, vehicles you can build, or how many types of ways you can build this car. No, you want to just do a simple multiplication like we have at the bottom of the board. So getting my fancy picture out of the way, very high-tech here, we have the fundamental counting principle says the number of ways a sequence of events, keyword on sequence of events, like you're choosing the color, then you're choosing the type of transmission, then you're choosing, what did I say, the engine? I think I left that out. That can occur. This could be for like how many different combinations does a regular master combination lock have. You can figure that out. This is found by multiplying the number of ways or choices each event can occur. And you saw that with the what did I have? 2 transmissions, 3 different engines, 5 different colors. Anything can match with anything else. Okay, well then it's 2 times 3 times 5. If there are, now this is sort of like a a definition for the fundamental counting principle that's all nice and wordy and hopefully, good to understand, but you might see a definition like this in your textbook. If there are m ways to do one thing and n ways to do another, then there are m times n ways of doing both. Now, this wording is if you only have two events or two things occurring with multiple ways of each one, but this can just be strung along for whatever, and you'll see this as we play the lottery. Now, that is the basic fundamental counting principle. You just multiply along all your different choices or different ways that certain events can occur. So if we get that, why don't we figure out if you play the lottery? Don't really think it's a great idea because I know my math, but hey, you can't win if you don't play, right? So let's play the lottery. So your state has a lottery that asks you to pick 6 numbers 1 through 53. Well, how many ways can 6 unique numbers come up? So you turn the TV on and they're like, today's lottery, and they got these machines and the balls are flying all over the place, and they start coming out and they go through that tube one at a time, right? And they don't replace these numbers back in the box or whatever machine it is that's blowing air all over the place, making these lottery numbers come up. So you have 6 unique numbers. One number cannot be played or show up in the game twice. So as you're looking there and they got this tube, usually it's some kind of like box like this, and those things are not like that, but like that, and those things are bouncing around, and there's this big tube, and just think of that tube, and there's 6, places for those numbers to come up. There we go. And in the first space, every number is inside this machine, so any one of those 53 numbers can come up. And then there's only 52 left. So any of those 52 are going to come up next, and then any of the remaining 51, and then 50, and then 49. And I'm having to count down by 1 because we're not allowed to repeat these numbers in this particular example. They have to be unique. So we've got 1, 2, 3, 4, 5, and then finally our 6th number, any one of those 48 numbers can come up. Well, using the fundamental, principle of counting or counting principle, we know that for each of these events, there's 6 of them. There's 53 sort of ways or numbers that can come up for the first event, 52 for the second, 51 for the third, and so on. And we now know that we can just simply multiply those together. So right off the top of my head, 53 times 52 times 51 times whatever, da-da-da-da-da, comes out to 1, 6, 5, 2, 9, 3, 8, 5, 600. I almost kept staring at that number long enough to finally memorize it, make you think, ooh, wow, he can do all that in his head. So there are 16, let's see here, this is hundreds, thousands, millions, billions. There's 16,529,385,600 ways that 6 numbers can be chosen from 53. Awesome. Not really, because why would I buy a lottery ticket if my chance of winning is 1 out of 16.5 billion? And then you go, well, wait a minute, that seems like a really big number. That can't be right. So you go to your, I live in Florida. You can go to the, Florida State Lottery website, whatever that is, and look up the odds of winning these games. And yeah, indeed, this really is not the right answer. Now, the reason why is, well, you have to choose the right 6 numbers, but they don't have to be in whatever order they come up in the machine. Like if these are, that would be weird. If these are the winning lottery numbers, number 49 could be first and 53 could be next to last. I just need these 6 numbers, or any 6 numbers. They don't have to be in that order. Well, the fact that the order of these chosen 6 doesn't have to be the same means that your odds of winning are a little bit better than what we see here. But wait, You don't, again, have to pick the numbers in the correct order. You just need the right numbers. And I did say the odds of winning were, and I didn't write out a statement that was appropriate for the idea of odds. You have to pick one of those 16,529,385,600 different ways that these six numbers can come out of the 53, or at least, you know, a game might be designed that way if you're looking at the way that automobiles are crossing the finish line in a race, then the order would definitely matter. But in a lottery game, it doesn't. So this is in red because it's really not the odds of winning this particular game if all we have to do is pick the right six numbers, but not in a particular order. The odds of winning, the real odds of winning, well, you also need to figure out how many ways these winning numbers can show up. And this isn't ultimately going to be the formula for the number of combinations, but I think it just kind of makes sense if we're developing the idea. So let's just say, for an example, the winning lottery numbers are 2, 21, 35, 37, 49, and 51. Oh, and by the way, we may not know it yet, but this process I did here was the number of permutations, where the order matters. But we got the numbers of 2, 21, 35, 37, 49, and 51. Those are the winning numbers. And let's say that you picked those six winning numbers. Well, when you're watching this come out on TV, after you stop screaming and you play it over again, any one of these six numbers can come up first. Now, we already know there's a bazillion different ways that these six numbers can be chosen out of the total of 53. If the order does matter, but any one of those six winning numbers, if this is the winning series, if this is what you got on your ticket, well, any one of those six can come up first, just like any one of the total of 53 that was in that machine could have come up, okay? Again, I'm just trying to figure out this idea of not having to pick the winning numbers in the right sequence. So any of these winning numbers could come up first. And now we can't repeat any numbers, so now there's only, let's say the 21 came up first. Now there's only 5 more left, so any of those 5 could come up next. Then any of those 4 could come up next. And then 3, and then 2, and then when there's only one winning number left to come up, well, then there's no choice there. It's just going to be that last one. Okay, so now this, 6 times 5 is 30. 30 times 4 is 120, and 120 times 6, I can do that in my head, is 720. Now that's over the number of what I'm going to just now say, permutations, the way that these six numbers can come up when order does matter, is going to be, what was that, 16,529, 385, and 600. Now it just happens to turn out that both the numerator and denominator are divisible by 720. So if we come in here and we reduce the numerator by, if I can write the 7 first, 720, and reduce the denominator by 720, we're going to get an odds of winning, which is, where is my correct set of notes here? 1. 720 divided by 720 is 1, and this huge 16 billion something divided by 720 comes out to be 22957 and 480. So our odds of winning the lottery game, if we don't have to pick the six numbers in the correct order, is 1 out of 22,957,480. So the number of combinations of six numbers chosen out of a total of 53 is, there's a total of 22,957,480 combinations, where the order of those six numbers does not make a difference. The number of permutations, if the sequence did make a difference, is quite a bit larger, which is, again, that 16.5 billion roughly that we had in the first place. So that is the difference between a permutation and a combination. So let me get this out, add a few more notes, give you a proper definition and some formulas, and finish up with 2 last examples. So our formulas, permutations, well, no item can be used more than once, like our lottery numbers, and the order of arrangement of our items from n matters. That would be NPR is equal to n factorial over n minus r. And the factorial, don't forget, 5 factorial is 5 times 4 times 3 times 2 times 1. Or maybe I should be counting that other way around. 5, 4, 3, 2, 1. And then you multiply all those numbers together. And don't forget 0 factorial, by definition, is equal to 1. And the number of combination, well, again, no item can be used more than once. And the order of arrangement of our items, that would be like, again, our 6 lottery numbers, from n, the size of the population you're pulling from, which could be like your 53 lottery numbers that were in that thing just flying around, waiting for the 6 winning lottery numbers to come up. The order of that arrangement does not matter in a combination, and the formula is NCR is equal to n over n minus r over r with all those factorials. Okay, and you'll find these commands in your calculator under the math probability menu, probably, if you have like an 84 or Inspire. Now, why did I go through that process of talking about playing the lottery and just sort of discussing our way through those scenarios? Because, well, we have a lot to memorize, and these formulas, don't really get used that much unless you're in a particular, probability area of mathematics. And I just wanted to show you that, these great that you know these, but we figured those problems out. The number of ways 6 numbers can come up out of 53 when the order does matter. Didn't realize that's what it was. And then we finished off with that example where, oh, no. Those 6 numbers don't have to show up in the exact order you picked them. And we talked about the number of combinations. Well, let's see. The number of permutations is n factorial. Now that's going to be, let's see, with that lottery and the 53 numbers in the machine all going crazy all over the place, that was any one of those 53 numbers could come up. That's n factorial. N, 53 numbers in that machine popping around. And then the denominator is n minus r. Well, we were talking about, and right now I'm doing 53 NPR 6. How many permutations of 6 numbers can there be when you're pulling from a total population of 53 of them? I don't know why I made the 6 so much bigger than the 53. So that would be 53 minus 6. Factorial. Well, 53 is, whatever. 53 times 52 times 51 all the way down to 1. And 53 minus 6 factorial, well, that's 47. How am I going to do this? Let's see here. 53 factorial is 53, 52, 51, 50. I'm going to run out of room, I think. 49, 48, 47, 46, 3, 2, 1, and then the denominator, I'll have to erase that in a minute. The denominator, this formula, this permutation formula says 53 minus 6 factorial. Well, that's 47 factorial. Well, 47 factorial is 46, excuse me, I did say 47. 47 times 46 times 45 times, counting down by 1 until you get to 1. All of a sudden I can't think and write at the same time. Well, if I go 53 factorial and I count down by 1 until I get to 1, and if I start at 47 factorial and I count down by 1 until I get to 1, 47 all the way down to 1 is going to cancel out with all of these 47s down to 1. Well, 53 times 52 times 51 times 50 times 49 times 48, that's just, well, that should be crossed out as well. That's just what we did in the previous screen, developing the number of ways 6 numbers can be chosen from a total of 53 just using that counting principle, that fundamental counting principle. So this idea of just having to fill up 1, 2, 3, 4, 5, 6, empty spaces where any of those 53 can come up, any of those 52 can come up, 50, 50, 49, and 48, we sort of did the permutation formula without even knowing it. So we can kind of figure these out on our own using a little bit of common sense. Then we talked about that, oh, well, wait a minute, these are all the different ways 6 numbers can come out of 53 when the order matters, but then we sort of just said, well, let's just pretend these are the 6 winning numbers and talk about how many ways those 6 winning numbers can show up, one of those combinations out of these permutations. And that formula is n factorial over n minus r factorial times r factorial. Well, that means that we're going to have, if we're doing 53 NCR6, well, n factorial, how large is your population, if you will? So 53 factorial over n minus r. So that's going to be, again, 53 minus 6 factorial. But now it's times r factorial, and we're choosing those 6. Now this is actually upside down from the way I did this in the previous screen, because just that idea of talking about odds of winning, it's just natural to me to think of that being the other way around. But this is just the number of combinations, and then you're going to pick one of those combinations to get your odds. Well, 53 factorial over 47 factorial, we just canceled that out. That's the same as we have up here, is 53 times 52 times 51 times 50, 49, and 48, and then that 47 down to 1 had already canceled out with that 47 factorial in the denominator. And here we have the 6 factorial, which is 6, 5, 4, 3, 2, 1. So maybe we've never seen factorials in combinations, and we still have the same looking math, except I had this upside down on the other screen because of talking about odds of winning. We kind of figured these out on our own without knowing these formulas. Now, it's nice if you know them, and the work goes a little bit faster if you do, but, we can think our way through these problems a little bit, right? So now, our last 2 examples, I'm going to verbally speak through them, and we can see this work for these formulas now, and so I'm just going to kind of explain how you would think about these and start them, and then I'm going to stop the video, walk off, and I'll be done. And I'll show you the solutions just before the video ends, worked out. You're choosing 3 people from a group of 20 to be a part of a committee for whatever, I don't know, school safety or something in your business. How many ways can you select 3 people? Well, think about the scenario. Is it going to matter what order these 3 people out of the total of 20, is it going to matter, or is it not going to matter? Well, if we were talking about picking, I don't know, you have 20 actors and you're picking 3 of them to play certain parts, it would certainly matter, which person you pick to play which part, because they have different lines to memorize. But in this case, if they're just going to a committee and they're all going to kind of just work together and have no particular job at hand, I mean, they're going to have some kind of goal as a committee, but one person's not the boss and one's the secretary and one's the whatever, they're just going into a committee, then it doesn't matter how you pick these 3 people. So that is going to be 20 NCR3, and I'll show the steps for that solution as we finish up the video. It's going to look just like it is over here. In a race in which there are 18 cars, how many ways can the first 3 cars cross the finish line? I kind of wanted to do like a NASCAR race where there's, I don't know, like 40-something cars, or endurance racing or something like that. Let's just think of this as a small F1 field, because these numbers get big really fast. So we have 18 cars in the field. They're going around in a loop or in the road course or whatever. How many different ways can we finish or fill the first 3 spots, the podium, if you will? Well, there's a huge difference between coming in first, second, and third, right? So in this particular case, the order in which these 3 cars come in out of the 18 is a huge difference. That's definitely a permutation. So that's going to be 18 NPR with a 3. And we're just going to work these formulas out, but I hope that seeing how multiplication cancels and how factorials works is kind of evident from these 2 problems. So I'm Mr. True. Thank you for watching. Bam! Go do your homework.